Yeah. um, in last two classes, we looked at the examples of phase diagrams of two different systems. One is water and the other is sulfur. And the commonality between those two is that both were single component, one component systems. Now onwards, we are going to study two component systems. What are these two component systems? You know, uh, water had a single compound in all the phases. This is not H2O. And even sulfur had a single compound in all the phases. Sulfur, element sulfur. But in two component systems, there will be two distinct components, two chemical species in all the phases. And as you know that when there are two components in a system, and when we are applying the Gibbs phase rule to calculate the number of degrees of freedom a system can have when it is in equilibrium, we get different results compared to one component system. What is the different result? Apply the Gibbs phase rule. F is equal to C minus P plus 2. Number of components here is 2. Please remember we were having 1 for one component system in our previous examples. So F is equal to 2 minus P. P is phase. Now, Gibbs phase rule can be applied for any region of the phase diagram, is it not? It can be applied to an area, to a curve, or to a point. Now, let us consider all the components or two components of the system are in a single phase. So to that phase or in a single phase, to that phase, when we are applying the phase rule, P should have the value of 1. So P is equal to 1 plus 2. And now we get F is equal to 3. So how many number of degrees of freedom are there? 3. Which are those? Of course, if the value of F is 1 or 2, what do we mean? It is either temperature or pressure, or both, sometimes temperature and pressure. The additional 3. So the variables now are along with temperature and pressure. Composition also becomes a variable. So P, T, and C. Please note the difference between two capital C's here. In the Gibbs phase rule, capital C means component. Here, capital C means composition of the phase. What do you mean by this composition of the phase? For example, if you can take a liquid mixture with some 20% alcohol and 80% water. So when we are telling the concentration of alcohol in that percentage, 20%, that becomes a composition. Okay, and components means in the context of Gibbs phase rule, components means the number of minimum chemical species we require to define the system or to define all the compounds of the system. That is component. Anyways, so we require three variables: pressure, temperature, and component. So how do we represent? Using a graph. Essentially, a phase diagram is basically a graph. Then we require how many coordinates? 3 coordinates. One belonging to pressure, the other to temperature, and the last one for to the composition. But of course, I'm not telling it is impossible to construct a 3 coordinate graph, 3 axis graph. You can. But for our ordinary usage, regular usage, and when we are working on papers, we are learning in classrooms, you write down on paper, I write down on board. So they're all two-dimensional materials, what we are using for our learning. So how to now represent this three-dimensional graph? Difficult, right? Almost impossible. So what we do now, what we are going to do is, we are going to omit, or we are going to exclude a variable from the system. What do I mean from this? Now there are 3 variables: pressure, temperature, and composition. Look at the system. For example, you are studying a system of alloys. Okay, alloys. And what is an alloy? It's the uniform mixture of homogeneous mixture of 2 or more metals. Let us say 2 metals we are mixing and making it an alloy. So in such cases, when we are working with metals and solids, basically, the vapor phase can be neglected because uh, it is very difficult to vaporize a metal, is it not? And when we are studying the system, the vapors are not formed within the range of temperature we are considering. It is not that we are not, it is not that we are just neglecting. They are not formed even. So they are not formed within the range of temperature we are working with. So uh, the variable pressure becomes a bit trivial in this case. Why? Pressure is significant when we are dealing with gases, when we are dealing with vapors. Nobody tells the pressure of solid, the pressure of liquid. It's the gas pressure we deal with always, is it not? The pressure of atmosphere is due to the gases in the atmosphere. Okay, fine. So now, so we can conveniently, without sacrificing some scientific value, scientific information, to neglect this pressure variable. So when we do that, what happens? A graph now need not have three dimension, in the sense three coordinates. It can still have only two coordinates. Which are those two coordinates? One is temperature, the other is composition. Anyway, pressure we have neglected, we have omitted. So we are not looking into the effect of pressure on the system at all. And of course, it's not just we are not looking into that. We are not working in that high temperature range where the metals vaporize and the pressure values become significant. Okay, so pressure we have omitted. So now the variables essentially reduce to two. Happy, right? Because now we have only two variables, we can conveniently construct a graph out of it. So now such phase diagrams or such systems in which one of the variables, mostly it is pressure, is not considered, is ignored, are called condensed systems. And now we have an phase rule accordingly modified for the condensed systems. We know F is equal to C minus P plus 2. And what is the two number there? One is pressure, the other is temperature. When we derived Gibbs phase rule, the two variables, thermodynamic variables, we fixed as pressure and temperature. Now, since we are removing pressure from that system, the phase rule gets modified as F is equal to C minus P plus 1. Okay. And this phase rule becomes the condensed phase rule or reduced phase rule. Right? General phase rule is F is equal to C minus P plus 2 to represent variables temperature and pressure, whereas F is equal to C minus P plus 1, where 1 is simply the temperature. Therefore, this becomes the condensed phase rule. Now, the condensed phase rules is important. In fact, when we are dealing with alloys, systems alloys, we are using the condensed phase rule, not the general Gibbs phase rule, condensed Gibbs phase rule. Now, two component systems. Come back to this two component system. And they are further classified into three different types. The simple eutectic systems and the systems which have compounds with congruent melting points, formation of compounds with incongruent melting point. Now, in this class, we are studying in detail a simple eutectic system. Now, what are the simple eutectic system? As the name suggests, it is simple. Why is it simple? Because first of all, it is simple because the two components in the system do not chemically react with each other at whatever temperature. Do not chemically react with each other. So to that much, our job has become easier, is it not? So we are not dealing with formation of some new compounds when we increase the temperature or decrease the temperature and so on. Therefore, in simple eutectic system, the first criteria is they do not react with each other. They are chemically inert to each other. And then that is fine. That is one, because that is what simple means. What do we mean by eutectic? This eutectic is maybe I think it's a I feel that it's a very new term to you. Is it not? Eutectic you may not have heard of in your previous semesters. So eutectic means the verbal meaning of it is easy melt. So eutectic systems are those which form an alloy which can be melted easily, basically. So what do we mean by this melted easily? So the okay, uh, not go uh, not understand this in the context of phase diagram too much. Simply, we'll just understand like that. What do you mean by melted easily? Melted easily means uh, now I have two metals A and B. Example: A has a melting point about 400 degrees Celsius and B has a melting point of about 800 degrees Celsius. Pure A and pure B. Now I'll form an alloy out of this. How to form an alloy? I have to mix A and B in different proportions. Is it not? So maybe some 30% A and 70% B I have taken. And I have formed an alloy. Alloy is also a solid, right? And what is the difference now? Alloy contains two metals now in a homogeneous form, homogeneous mixed form, two metals. Okay, fine. Now we find out the melting point of this. It could be 200. It could be, I'm not saying it is always, it could be 200. Now, don't you think this 200 melting point is way low than 400 and 800 of the pure metals? Of course it is. So what's the point now? Therefore, uh, you have an alloy, you have a mixture of some composition, you have an alloy of some composition which has a melting point lower than that of pure A and B and is easy to melt. See, when is a compound easy to melt? When it has low melting point. Okay, therefore eutectic systems are those systems which form alloys like this, which have a lowest melting point compared to compared to pure metals as well as alloys of different compositions. That is what eutectic means. So what are the features of simple eutectic systems? First, they are chemically inert to each other. Two components do not react with each other. Second is they form an eutectic composition, eutectic mixture, which has the lowest melting point, which can be easily melted. And third is very important feature, particularly in terms of understanding the phase diagram next, is that they are homogeneous in the liquid melt. So two metals A and B mix with each other when they are melted and formed and melted and made into a liquid mass. Okay, this is called melt. Right? When we are talking about the eutectic systems, the liquid phase is called a melt or liquid melt. So in the liquid melt, there will be two metals which are miscible completely with each other. Whereas in the solid state, they are immiscible. Okay, in the solid state, they are immiscible. We will understand this a bit more when we look into the phase diagrams, when we look at the phase diagram. So such systems are called eutectic systems. Okay, fine. So the one eutectic system in your syllabus is the lead silver system. And since now we will have the phase diagram of this, okay, this O has come here. It's fine, no problem. 1 second. Let me correct this. Okay, uh, fine. So as always, phase diagram has come up. Now, a phase diagram, any phase diagram has three important features: areas, curves, and points. Now, this is a phase diagram where some color coding is there to make you understand better. Two metals, A and B. One is the silver, which has a melting point of 961 degrees Celsius, pure silver, and the other is lead, pure lead, which has a melting point of 327 degrees Celsius. Fine. Now, This phase diagram graph contains two axes. The one is temperature, the other is composition. Please note the difference of this phase diagram. In the water and sulfur system, the axes were temperature and pressure. Temperature and pressure. And temperature was on the x-axis, pressure on the y-axis. Look at the difference. In this condensed phase diagram, since pressure we have omitted from our discussion, or we have excluded from our discussion, pressure is no longer a variable in our graph. Therefore, the two variables are temperature and composition. On the x-axis, it is composition. Y-axis, it is temperature. So what do we mean by that composition? Simply, what is the percentage of lead and silver you have taken to form a alloy? Fine. Okay. So in phase diagrams, when you are constructing, when you are wherever, not just in phase diagram, even in our vapor pressure curves, graphs and all, the composition axis will have two origins. The first origin, there will be a pure component 1. In the second origin, it is pure component 2. For example, here on the origin, this is the origin. What is the composition of the alloy? It is not an alloy now. It is simply the silver pure metal. You have one more origin here where there is lead pure metal. In between these two origins, you have the axis, you have the line, which represent points, and every point corresponds to composition of some composition. For example, I have taken a point here. What is the composition of the alloy? 2.6% silver, 97.4 lead. I mean, I hope you understand an alloy, right? Alloy is not a pure metal. You have one more metal mixed with it. It's an alloy. Okay, so any other point represent alloys, different composition. Now, if you take the you can bisect this line and take the midpoint of this line. What is the composition there? 50%. Is it not 50% lead and 50% silver? So then now how to construct this phase diagram? It is easy, much easier, because there is no pressure variation here. It is much easier. All that you have to do is you record the melting point of silver. So how much is that? 961 degrees Celsius. Plot it on the temperature axis. In fact, to specify this, I shouldn't call this even a temperature axis. It should be a melting point axis, basically. What is the melting point of Ag? 961 degrees Celsius. What is the melting point of pure Pb, lead? 327 degrees Celsius. Fine, no problem. Now, you prepare alloys of different compositions. Prepare alloys of different compositions and start recording the melting point of those alloys. All the values of the melting point you plot in the form of a graph. When you do this, you see that it assumes a shape like this, almost a wing-shaped curve. Is it not? V-shaped, very bent V-shaped or a wing-shaped curve. Okay. Now, simply as you go towards right on this axis, what happens? In the alloy, lead percentage increases. As you go like this, in the reverse direction towards left, your Ag percentage increases. Because finally, at this point, Ag should be 100%. And at this point, Pb should be 100%. Is it not? So, this is what the composition axis is. Is it not? Don't you think it is easier to construct this phase diagram? Yes, of course. In fact, since it is a bit easier and there is no complication of measuring the pressures, in your practicals you have construction of phase diagram for an eutectic system. Of course, not with silver and lead. I mean, we can't give you silver for your practicals, right? It is too costly. We have two organic compounds in your practicals there. One is the naphthalene, the other is the biphenyl. So you can construct, okay. So how is the experiment done? What is the procedure of that experiment? As I explained now, record the melting point of pure naphthalene. Record the melting point of pure biphenyl. On a graph sheet on the melting point axis, temperature axis, mark the melting points. And now you weigh weigh different amounts, different weights of naphthalene and biphenyl into a test tube. Melt it, melt it. Both will melt, right? And solidify. When you cool, it solidifies. Now the mass which is remaining in the test tube is not a pure compound because it contains both naphthalene and biphenyl. In that case, we don't use the term alloy. It is simply a mixture. Why? Because alloys are meant for the mixtures of metals. Fine. So every alloy, you record the melting point. The melting point, as the percentage of silver decreases in the alloy, the melting point simply comes down, 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 and reaches a minimum. Let us talk about this minimum later. Similarly, as the percentage of lead decreases in the alloy, there is a decrease in the melting point also. So what is this AO? AO. AO is nothing but the freezing point curve of silver. Freezing curve of silver. Melting and silver. Why is it freezing? If you look at from the liquid melt side, it is freezing. If you look at from solids point, it is melting. This is the freezing point curve of or freezing curve of lead. Okay, fine. Now, once the alloy melts, what does it form? A melt, liquid. It forms a liquid. That is the liquid phase here. And as I told you, in the eutectic system, a liquid is homogeneous. Both lead and silver are mutually soluble, miscible in this liquid melt. Okay, liquid melt. Now, okay, fine, no problem. Now we will look at look at this from the direction of freezing. Yeah, what happens when the liquid melt freezes? What happens when the liquid melt freezes? It should form a solid. What solid it forms? Okay, now let me consider. I have taken about 90% silver and 10% lead. So melting point is somewhere here. Melting point of that alloy is here of 90% silver and 10% lead. Okay. So once this is melted, you get a homogeneous liquid. You freeze that liquid, cool that liquid. What should happen? You should get solids back, solid back, but it doesn't happen. You don't get a solid which is homogeneous. Homogeneous solid containing 90% silver and 10% lead. Instead, your liquid, from the liquid melt, solid silver comes out, precipitates out, and the remaining will be lead in that. In the remaining liquid will be lead. Okay, so this is what, see, in our previous examples, water and sulfur, every area represented a single phase. But in this, although this AO and some letter maybe X here. So AOX, X and Y, this is probably. This AOX is of course an area in the phase diagram. But unlike water and sulfur system, this area is not composed of single phase. It has two phases, liquid and solid age. Okay. Similar thing happens here. As you cool melt, which is enriched in lead, for example, when the freezing starts, maybe for example, I have taken 90% lead now and 10% silver. So the melting point is somewhere here. So when you melt, it forms an homogeneous melt, liquid melt. When you cool it, as it freezes, lead separates out, pure lead, and the liquid is left behind. Okay, so again, this BOY, this area is not containing single phase. It is made up of two phases, the liquid and the solid. Okay, so that's all the features of this phase diagram is. The one interesting feature of this phase diagram is this O, point O. Okay, in our water and sulfur phase diagrams, every point O, points like this represented triple points. Is it not? Water had one triple point, sulfur has three triple points. But here we don't use the term triple point because the phases are not in equilibrium in the true sense. Of course, this phase you can take as liquid phase. But when you come here, it is not a solid phase containing components. It is again a heterogeneous phase, right? This is having liquid plus solid sulfur and solid Ag. And here it's again a heterogeneous phase, liquid plus solid Pp. Therefore, what happens? This is not called a triple point. It is simply called an eutectic point. So what is this eutectic point? As I told you, eutectic means easy melt. What is the significance of this eutectic point now? And even the composition of this eutectic point I have given. It is 2.6% Ag and 97.4% lead. So this alloy of this composition melts at what temperature? At 303 degrees Celsius. Okay. This is the lowest melting point possible for the system. That means you prepare, you consider pure metals melting point, 961 for silver, 327 for lead, and you consider the melting points of any alloys on this composition axis. Any composition alloy of any composition, this composition will have the lowest melting point, and that is called the eutectic point. And the corresponding composition is called the eutectic composition. Okay, fine. So now, when I call this an eutectic composition, that is fixed. Only the composition with this, only the alloy with this composition has the lowest melting point. No other composition will have melting point equal or lower than 303 degrees Celsius. It will always be higher than 303 degrees Celsius. Okay, so this is how a eutectic point becomes significant in our whole study. Okay, fine. But what is the significance of eutectic point? Why should I prepare an alloy with low melting points? That's the question, right? Because, I mean, from the application point of view, when we are visualizing, in fact, don't think that Gibbs phase rule, what we are talking of, is a very dry subject. Means that it is very theoretical, and finding an application of that in real life is difficult. It has a lot of applications, particularly in metallurgy and alloy science. In the alloy technology, phase diagram has lot of applications. So the eutectic point, this is the composition. You require metals which melt at low temperatures also. It's not metal always. For all applications of metals are very hard and very high melting. There is one application of this directly is in the electric fuses. I hope you know what is a fuse. It is nothing but an electric circuit breaker, is it not? When the voltage fluctuation happens, when there is high voltage in the line, so the fuse melts and the circuit is broken. So that therefore your home appliances are protected because the current is cut off, the line is cut off. So how this fuse works? Fuse is basically an alloy. Okay, and you also know the heating effect of electric current. So when the electric current is flowing through conductors, it also heats that conductor. So when it flows through the fuse, it also heats the fuse. But when the voltage is stable and under control, there is no so much heating effect. So the fuse doesn't melt. When the voltage goes above the threshold, that threshold would have been fixed by the engineers. So if the voltage goes above the threshold, what happens? The heating also increases. So the temperature of the fuse increases. And if you have made the fuse from a low melting alloy, then the fuse melts and the circuit is broken. Because for the electric current to flow, it has to be a solid conductor. When it is melted, that's the place where the circuit is broken. Okay, fine. Now, for example, if you are developing if you want a material to develop a fuse, you are not going to look for material with very high melting point, right? So in that case, very high voltage is required for heating it up to the level of its melting point. So that then uh, your objective is not served. Therefore, that is one application where you are looking into materials with low melting point. Okay, so there the material has to be a conductor, so it has to be a mixture of metals and a low melting point. So where can you find it? You cannot find in pure metals. You have to make an alloy. So now that's what I told. So whichever alloy you have to prepare, you have to first construct the phase diagram of that alloy and see where it is, where its eutectic point is, and then devise your application of that alloy accordingly, according to your phase diagram. Fine. So what are the features now in our phase diagram? The area, area AOB is the only area I'm considering. Yeah, I'm not considering AOX. As I told you, this area doesn't encompass a single phase, homogeneous single phase. So apply this phase rule to that area. Fine. See, after we define our system, and then we start applying Gibbs phase rule to all the features of the phase diagram, to the areas, to the curves, and to the point. Now, since we are considering a condensed phase system, reduced phase system, the reduced phase rule or the condensed phase rule is considered. F is equal to C minus P plus 1. So for area, the number of components in that area were 2. Is it not? See this? Solid plus liquid. This area contains 2 components. Silver plus lead. Liquid contains lead. Here, liquid contains silver and solid has lead. So 2. If you do this, 2 minus 1 plus 1, F is equal to 2. That means the system is bivariate. So what do you mean by bivariate? Both temperature and composition have to be fixed to define the system. The area below the line AO and below the line PO and below the point O. Okay, so which is that? This is the area I'm talking about. Below 303 degrees Celsius, simply for this area, the highest temperature is 303 degrees Celsius. Below 303 degrees Celsius. Okay, has 2 phases in it. So apply the phase diagram. Gives phase rule. C minus P plus 2, 2 minus 2, F is equal to 1. So the number of degrees is 1. It is univariant. Okay, fine. 2 phases I told you. Which are those 2 phases? Solid Ag and solid lead. And this curve AO, I explained what is freezing point. We just have to calculate the number of degrees of freedom for these curves. So C minus P plus 1, F is equal to 2 minus 2 plus 1, F is equal to 1. So again, the curve has come as a univariant entity. That means even in our water and sulfur system, a curve was univariant. Is it not? Here also the curve is univariant, although we have applied different phase rules. In that, the formula was F is equal to C minus P plus 2. Here the formula is F is equal to C minus P plus 1. In spite of this modification, still the curves are remaining univariant. What do you mean by univariant? Either one of the variables has to be fixed. Either temperature or composition must be fixed to define the system. It simply means you cannot vary both temperature and composition simultaneously. You have to fix one and vary other. Okay. Now, fine. So finally, I just want to tell you one thing. Eutectic point. So what is this eutectic point? As I told you, eutectic point represents the point at which the minimum melting point is observed for all the possible compositions of the alloy. Minimum melting point. So that is what eutectic point is. So in eutectic point, apply the phase rule. F is equal to C minus P. How many components? 2 always, because we are considering a 2-component system. Yeah, it is always 2 minus 3, number of phases 3, and plus 1, F is equal to 0. Which are those 3 phases? Which are these 3 phases? One is the liquid phase, melt, homogeneous phase, and this one, and this. That's a solid Ag plus solid Pp. Liquid, one phase, solid Ag, the other phase, solid Pb, the third phase. Therefore, number of phases becomes 3, F is equal to 0. As usual, it is non-variant. Similar result was obtained for the triple points of water and sulfur system also. They were also non-variant. So the point O is called eutectic point. So in eutectic point, it has 2 coordinates. One is the temperature coordinate and the composition. So what is the corresponding value of the temperature for eutectic point? That becomes eutectic temperature. It is 303 degrees Celsius for lead silver system. What is the corresponding composition? It is 97.4% lead and 2.6% Ag. This is called eutectic composition. I hope maybe in this example, it would be clearer what non-variant means. Non-variant means. See here, can you have variation in the composition? No, because that is fixed. What is the, or how much is that? 97.4% Pb and 2.6% Ag. Any other composition, eutectic point is deviated. Is it not? There will be no eutectic point for any other composition. Can you vary the temperature? No. 303 degrees Celsius. Any other temperature, it is no longer a eutectic point. Therefore, that is the meaning of non-variant. When you have a phase diagram, both the coordinates variables, either temperature and pressure in the one component system or temperature in composition in this system, have to be fixed. Only single value of temperature, single value of pressure in that system, in those systems. Single value of temperature and single value of composition in this system. That is called non-variant point. There is no freedom at all. There is no freedom for you to vary the variable. They have to be fixed. Okay. So what happens below this eutectic point? Below the eutectic point, the eutectic compound and the metal solidify. What do you mean by eutectic compound? A compound with this composition is called eutectic compound. Okay, this is the alloy or eutectic alloy you can call. Eutectic compound means the compound with this composition and the metal solidify. That means there is no liquid phase at all below 303 degrees Celsius. That's the minimum melting point. Below that, it doesn't melt at all. Below 303 degrees Celsius, none of the compositions melt. They are always solids. Okay. Now the final slide for this presentation. What is that? Patterns and process of desilverization of argentiferous lead. So you have in fact studied one more process of desilverization of argentiferous lead. Where was it? In the solutions chapter, where we used solvent extraction method to purify silver or to extract the trace amount of silver which was present in the lead. So the lead was melted and molten zinc was added. Since the silver was 300 times more soluble in zinc, it distributed in such a way that it went into zinc layer, and the zinc, when evaporated, gave you pure silver. But in Pattinson process of desilverization, we use phase diagram for this process, not the solution solvent extraction, phase diagram. So now, what is the point here? For example, you can have a lead ore example which has trace amount of silver. Here example lead. So you melt that. Maybe it has 2% lead, 2% silver. Let us think it has 2% silver. So you melt it. So what happens when you melt it? Okay. What happens when you melt? Anyways, what happens when you melt? It forms a homogeneous mass. What is the percentage of silver in that? 2%. Let us think it is 2%. And then start cooling it. start cooling it. Start cooling it. Now, when you reach this point, which is the point on the OB curve, that is the freezing curve of lead. What happens when you, this is very important now. This is where the understanding of the chemistry comes into picture. What happens when you reach this point? Solid lead separates out, leaving behind the silver, leaving behind the liquid. Liquid also has some amount of lead in it. It is not pure silver liquid. But since some appreciable amount of solid lead are separated out, the liquid which is remaining now, does it contain the lead in the same composition as you started with? No. Definitely lesser amount of lead is there in this liquid because lead has precipitated out. A lot of lead has precipitated out, separated out. So this liquid now is rich in silver. Okay. Liquid now is rich in silver. So you can do this cooling. You again take this melt, start melting. You solidify this or you freeze again. Further you freeze. As you go on freezing, what happens? Every time you freeze, some amount of lead separates out. And finally you reach this point. At this point, what is the composition of silver now in this melt? What is the composition? It is 2.6 silver and 97.4% lead. Maybe you started from 1% silver. Finally, you have enriched to 2.6% silver. So that is what Pattinson process is. Process of raising the relative proportion of silver in the alloy is known as Pattinson process. But you cannot raise it beyond 2.6%. So you can enrich the amount of silver in the lead ore only to the extent of 2.6% because that is the limiting value. Composition with, this is the eutectic composition. Fine. So this is called Pattinson process. So that's it. So about two-component eutectic system. I hope things are very simple here. All that you have to know is the alloys compositions and how the melting points of that alloys vary.